Hello everyone, welcome back to our lectures of the partial differential equations, and today we're going to continue to talk about solving our partial differential equations using the separation variable of method. In the previous times we have only talked about how to solve with the heat conduction, with the insulated ends, and the temperature, the zero temperatures at the end, at the boundaries of our rods. And you can see like how we approach it using the same method. One method, only one certain eigenvalue was acceptable, such as the lambda greater than 0. The other one was acceptable, lambda equal to 0 and lambda less than 0. And now we're going to talk about that all the eigenvalues that are acceptable, and you will see how. Suppose we have a wire. So let's say the wire have a length of 2L. Now why I choose 2? Because it simplifies, there are some cancellations. Now suppose we have that straight wire and we bend it to make it a circular. Okay. So now let's choose this point to be x equal to 0. Here above it's x equal to plus L, below is negative L. Okay, so since the length is 2L, right, therefore our circumference is equal to 2L, therefore our radius is just equal to L over pi. Now we assume that the wire is thin enough so the temperature in a wire is constant along the cross section of the band. So the heat flows, and we assume like it's a very thin, not like my drawing. The drawing doesn't show it's thin, but it's very thin. It's just a one straight line. So another thing we have to assume that our wire is tightly connected here at the ends, or here, doesn't matter. So the temperature right here above x equal to L and x equal to negative L is the same. And not only the temperature, the heat flux is also continuous at that positions. So they are the same. So we can assume the wire is tightly connected to itself. Now let's create our PDEs. So it's a heat, again it's our heat is flowing and the temperature is changing, maybe with respect to time or along the position. So the second order derivative temperature, and now there's no any additional source that provides the heat, so therefore our PDE is just gonna be partial U partial T, that's equal to our diffusivity constant, second order x squared. So that's our PDE. Now let's talk about our boundary conditions. So now the boundary condition, how they're going to look like. So first of all, let's talk about the temperature. Since they are tightly connected, so we expect that temperature at these positions must be the same. So we will say that the temperature negative L at certain times T is the same as the temperature L comma T. Now the second boundary condition will be not only the temperature is continuous, the heat flux is also continuous, meaning the heat that is flowing across these cross sections is the same in both cases. So that means in both points. So my partial U, partial X at X equal to negative LT is equal to partial U, partial X at L comma T. So that's my two of my boundary conditions, and then the initial condition that U of X 0 is just equal to f of X. Okay, initially the temperature distributes the function of f of X. So now let's solve it. Now, if you remember, our separation variable method can only apply if both our PDE and boundary conditions are linear and homogeneous, right? So, in our example, our PDE is homogeneous and is linear. But it doesn't look like that our boundary condition is homogeneous, but it is homogeneous. Why it's homogeneous? Because it's just a function of U. There's no like, it's linear operators to our unknown function. There's nothing like wrong with this picture. It's still a homogeneous. Because you can think of it as the U of negative LT minus U of L of T. Our function U, no operation applied to it, that's equal to 0. So this is homogeneous linear PDE and homogeneous linear boundary condition, so we can apply our separation method variable. So again, our product solution is that our U of xt is equal to 5x times g of t. Okay, so now let's look at each of them separately. So if I substitute this again, I will get the 5x times the partial g or partial t, that's equal to kg partial phi partial x squared. Now let's separate them. Now we get 1 over kg partial g partial t is equal to 1 over phi x squared, and that's equal to our eigenvalue, negative lambda. So therefore, the time dependence part this part is gonna be again the same. So our partial g partial t 1 over g is equal to negative lambda of k lambda. So my partial g over g is equal to negative k lambda dt, and I integrate both sides. Therefore I get natural log of absolute value of g, that's equal to natural log of absolute value of g, that's equal to negative lambda kt plus a constant, and therefore solving for g, our G is equal to a certain constant C times C of negative lambda kt. So that's our time dependence. So now let's look at the position time independence part. Now, since our time independence, we have second order differentiation of our phi that's equal to negative lambda phi. Now let's look at our boundary conditions. Applying the boundary conditions, we get that our u negative lambda of t that's equal to u that's equal to phi of negative L g of t, and our u lambda t is equal to phi of L g of t. So since these both are equal to each other, therefore our phi of negative L is equal to phi of L. So similarly, the other boundary condition. For the other boundary condition, so our d phi dx at negative lambda is equal to d phi dx at position lambda n. So now we have another PDE, and this is our PDE, ordinary differential equation with this two boundary condition. So again, let's solve our second order differentiation equation. So apply ansatz. Our ansatz is that my phi is equal to E of Rx. So therefore R squared E of Rx is equal to negative lambda E of Rx. So R squared is equal to negative lambda. Now let's look at the each conditions separately to see where this is take us, which eigenvalue satisfy our p partial differential equation. Now before we move on to determine of our partial differential equation, you can also think about that this temperature, we can have multiple boundary conditions in this case. The main reason is that, as you realize, since our heat is flowing around this wire, around this thin wire, so therefore anytime it crosses this point, it's gonna get the same change in u, change in t, or same change in u over change in x. Meaning that the temperature, our temperature is the same for any arbitrary point x equal to x naught, and now I can say the 2 pi, but we are talking about the length, not the angle. So in this case, our length, every time it crosses, it starts from here. After traveling with the length of the 2L, it comes back to here. So it still have the same temperature. So it's the same for x equal to x naught plus 2L. X equal to x naught plus 2L. Now let's determination of our boundary condition. So let's start. Case. So for the lambda that's greater than 0. Okay, the first case. where the lambda is greater than 0. Now, if the lambda is greater than 0, therefore our r squared, that's equal to negative lambda, our r is equal to plus minus I times square root lambda. So now therefore our ansatz is equal to constant 1 of e of positive I square root lambda plus second constant e of negative I times square root lambda. So therefore if we apply our boundary, so now applying to our Euler identity which we did previously, is just equal to another constant like d1 cosine of lambda Lx plus another constant d2 sine square root lambda x. So this is our phi look like for the lambda, for the positive lambda. Now let's apply our boundary condition. Now since our applying the boundary condition, now since our phi of negative L is equal to phi of L, therefore we have d1 cosine of lambda L plus d2 sine lambda L, that's equal to, now that's a for phi equal to L. Now for phi negative L, we get d1 cosine of square root lambda L minus d2 sine square root lambda L. Okay. Now all of this will get cancelled out. Since it's the same. This d2, so therefore d2 sine square root lambda L is equal to negative d2 sine square root lambda L. Now this is only possible if our constant is 0 or our square root lambda L is equal to 0. Lambda L is equal to 0. Now before we go, let's apply our second boundary condition. Now where our partial phi partial x at negative L is equal to partial phi partial x at L. So if I take the partial derivative substitute, I get negative d1 square root lambda sine lambda L plus d2 square root L cosine of square root lambda L. Now I substitute our negative L to the derivative, so it's going to be positive d1 sine square root lambda L plus d2 square root lambda cosine square root lambda L. There's a one mistake I did. Here. Now in this case this d2 cancel. Therefore our d1 square root lambda sine square root lambda L is equal to negative d1 square root lambda sine square root lambda L. Now this is up. Now we have both of the cases. We got that these two are equal to each other. So like if we take both of them one side, I get in both cases I get d2 minus t2 sine square root lambda L is equal to 0, or d1 sine square root lambda L is equal to 0. So both cases conclude one thing: if we're trying to avoid the trivial solution, that our eigenvalue is going to be L equal to n pi over L squared. So therefore, by summary, our phi for the positive lambda is equal to d1 cosine n pi x over L plus d2 sine n pi x over L. So therefore our positive lambda is our eigenvalue. So now let's look at the second eigenvalue, where the lambda is equal to 0. So now the case where our lambda is equal to 0. Now if our lambda is equal to 0, therefore my r is equal to 0. Now if my r is equal to 0, I have a repetitive solution. So therefore my phi has applying to my ansatz is going to be c1 plus c2x, just the equation of the line. Now therefore applying the boundary condition, that will lead me that c1 minus c2l is equal to c1 plus c2l. So therefore this is possible, my c2 is equal to 0. Now this leads that my phi is equal to c1. Now if I apply the second boundary condition, where my partial phi partial x negative lambda is equal to partial phi partial x of lambda, if I take the derivative of my lambda, I get c1 in both cases. So therefore my phi is equal to just c1. So both of them prove that this is my the lambda equal to 0 is also the boundary condition. So now let's look at the case where the lambda is negative. Now therefore my r is equal to plus minus square root negative lambda Now if I apply my boundary condition, now if I substitute, apply my answers, now my phi is just equal to c1 e of square root negative lambda x plus c2 e of negative square root negative lambda x. Now apply the boundary condition. After applying the boundary condition, now I got that my c1 e of square root negative lambda L is equal to c2 e of square root negative lambda L, plus, that's equal to c1 e of negative square root negative L, that's equal to c2 e of negative square root negative L lambda L. This is negative Why I keep messing this up. Now that's become positive. Now if I apply the second boundary condition, I get C1 square root negative lambda times E of square root negative lambda L minus C2 square root negative lambda E of negative square root negative lambda L. That's equal to negative C1 square root negative lambda E of negative square root negative lambda L plus C2 times square root negative lambda E of square root negative lambda of L. Now if I try to solve these PDEs, like if I try to solve it, I will get the trivial solution. So let's try how we can solve this. First, let me just name them equation 1 and equation 2. In equation 1, if I separate that, the C1 times E of square root negative lambda L minus E of negative square root negative lambda L, that's equal to C2 C2 E of square root negative lambda L minus negative lambda L. So now these two cancel each other. I get C1 is equal to C2. Therefore, if I apply a substitute to equation 2, I will get C2 square root negative lambda E of square root negative lambda L minus C2 square root negative lambda E of negative square root negative lambda L. That's equal to negative C2 square root negative lambda E of negative lambda L plus C2 square root negative lambda E of square root negative lambda L. Now this and this cancel, this cancel, and therefore my C2 is equal to 0. Therefore my C1 is also equal to 0. Now therefore the only acceptable eigenvalue is going to be positive and the 0 eigenvalue. Now let's apply our superposition principle. If we apply the superposition principle, so now applying our superposition principle shows that our temperature is equal to the constant that is responsible for my lambda equal to 0, and for the lambda equal to positive lambda, we get both sine and cosine. So therefore we have infinite series for cosine and then we have infinite series for sine times the time dependence of both of them. Now if we apply our initial condition, therefore for my initial condition, my function of x is equal to a of 0 plus the infinite series for a of n cosine n pi x over L plus b of n and sine n pi x over L. Okay, so now to figure out this constant, we have to apply the orthogonality condition. So now there's some orthogonalities. The conditions that will be helpful for us to solve. First of all, we are looking for the road going with the length of 2L. So we are looking from going from negative L to L. Now for our cosine n pi x over L with a different eigenvalue. If you remember, it's possible to get three answers. One of them 0, L, or 2L. Depends on the eigenvalue. We get 0 if we have a two completely different eigenvalue. We get L if both eigenvalues are 0. And we get, L if both eigenvalues are equal but they are non-zero. And we get 2L if both eigenvalues are equal to 0. For the sine, we still can have it possible, but we are able to summarize it in terms of this. L chronicle delta nm. If you don't remember our chronicle delta, it's equal to L times 0, 1 for 0 for different eigenvalues, for 1 if they both are not equal to 0. And then lastly, if we have mixed, so one is sine and the other one is cosine. In this case, no matter what the eigenvalue is, we will get the 0. So now we're going to multiply our eigenvalue, this cosine corresponding cosine or sine with the different agent of both sides and tries to solve it. So we can do both of them at the same time by summarizing two in one line. So negative L to L f of x. So either we multiply to cosine n pi x over L or sine n pi x over L dx. That's equal to, and now for the Riemann sum, we can combine this A0 with this one, and then we can separately do this one. So this is equal to Riemann sum n equal to 0, A of n times the integral negative L to L cosine n pi x over L, multiply either cosine n pi x over L or sine L dx, and this is equal to 1, oh no, sorry, not equal to, plus we still have the sine part. And pi x dx. Now we will apply the knowing our orthogonality conditions. So this will conclude us that our from negative L to L f of x. Now let's say if we multiply just cosine m pi x dx, now only we left with our a of n part, because our b of n, the sine multiplied with cosine, will lead us 0. Now will lead us 0. So therefore we're going to have a of m negative L to L cosine squared m pi x over L dx. Now if we just multiply the sine, now similarly we multiply the sine only, this cosine and sine will make it 0, and we have the sine squared, so it's going to be b of m integral negative L to L dx. Now because of this orthogonality we can determine our coefficient, so therefore for m equal to 0, so our a of 0 will be equal to 1 over 2L negative L to L f of x dx. My a of m is equal to 1 over L x, and my b of m sine m pi x over L dx. So here's my my coefficient, and this is the solution of my PDE with these coefficients. So this is how we solve for the circle thin disk. Everything was the same, just this one thing that we have to come out with this boundary condition, and this is which is still linear and homogeneous. And this is, we are concluded. The next one we're going to solve our first Laplace equation, and we're gonna introduce some qualitative properties in the Laplace equation, and in the future, for not right now but far future, I will represent some concepts like upper division of concepts that are useful in upper division or grad level of partial differential equations. Thank you so much, and hopefully you will enjoy this video. Bye bye.